Okay, there's one more data structure I want to go through here because it has some really neat properties. It's quite different from the other data structures we've seen because actually it represents a graph as a two-dimensional array. So let me explain what I mean. What we're going to do is have a row for each vertex in the graph, so I'll go ahead and set that up here. And also a column for each vertex in the graph. Just like that. And what I'm going to do is put a 1 in an entry if that vertex is a neighbor of the other vertex. And so here 0 actually is a neighbor of itself, so that'll be 1. And then I can ask, is 0 a neighbor of 1? Yes. Is 0 a neighbor of 2? Yes. Is 0 a neighbor of 3? No. So in that case, I'm going to put a 0 there. Is 0 a neighbor of 4? No. Okay. Now I'm going to do the same thing for 1. So is 0 a neighbor of 1? Yes. Is 1 a neighbor of 1? No. Is 2 a neighbor of 1? Yes. Is 3 a neighbor of 1? No. Is 4 a neighbor of 1? No. So let me just go ahead. I'll fill in the rest of this table for a second. Okay, so here's the completed version. Now let me go ahead and implement that in Python. And I'll tweak the thing we had before. Actually, here I'm going to use NumPy, numerical Python, because it's perfect for this. NumPy is designed to deal with matrices, or another name for a two-dimensional array with uniform shape everywhere. So actually, one thing I will change about this API, I'll specify the number of vertices ahead of time. And so what I'll do is I'll set up, I'll call it A for the adjacency matrix. Self.a is equal to mp.zeros, num vertices. So certainly there are versions of this you could make where you have, the capability to actually add vertices. Let me remove that capability for now, and I'll just implement the adding the edge capability and the neighbor capability. So when I add an edge, then I just have to set the corresponding row of A and column of A to 1. Now let me also, I guess I'll also assume here for the moment that U and V are ints, 0 indexed integers. So that I can actually directly index A here. Again, you could certainly convert from data that you have into an integer. You could uniquely assign an integer to each data that you have if you want to consider that data to be a vertex. But so with that loss of generality here, I'll just assume that everything is the integers like this. Okay, so what I'll then say is self.a at row U, column V is equal to 1, and then self.a row V, column U is equal to 1. So that's analogous to what I had done here before. Now to get the neighbors, what I have to do, this is somewhere in between the efficiency of what I saw before. What I'll have to do is loop through the row of V and collect all U's that are at 1. So I'll say, okay, naive starts off as an empty list, and I'll say for U in range self.a.shape1. So that's the number of columns. So I'm going to loop through all the columns, and I'll say if A v U is 1, naives.append U. All right, so then I'll just go ahead and return that. And actually, it's a set. I'll make it a set to be consistent with what I did before. So that's actually add instead of append. And for isEdge, actually this is going to be constant time, because what I'll do is I'll just go directly to the adjacency matrix, and I'll go to row U, column V, and then just to check things, this is an undirected graph. This should always be the case, but I'll make sure that they're both neighbors of each other. Okay, that got a little bit cut off there, but that's what I had written. Okay. So let's just make sure this still works. I'm going to rename this to adjacency matrix. Now I need to instantiate it with the number of vertices, so I'll go ahead and make that a variable here. I'll pass that along. And Actually, I don't have the add vertex method anymore, but I do have the add edge method and the get neighbors method. So let's see how that does here. Again, this is not called adjacency graph, it's called adjacency matrix. Oh, and I should have said here, this is an instance variable. So I should have said if self.a vu is equal to 1. Okay, good. So let's see here. 0 is a neighbor of itself, and 1, and oh, it looks like we missed 1 here. So what happened? Oh, well, this is a different graph. I changed the graph a little bit. I was just because I wanted to make a slightly different example. So give me a chance, and I'll clean this up and then check it. All right, so I cleaned that up, and when I run this now, I get the following, which does seem to be correct. Okay, so 0 has neighbors itself, 0, 1, 2, and 3. 1 has neighbors 2 and 0. 2 has neighbors 1, 0, and 3. 3 has neighbors 2 and 4, and then 4 has neighbor 3. Good. And actually, just to check, we can dig into the data structure a little bit and print out the adjacency matrix. And just check against what I had drawn before. And if I check, I'll see that this is the same. Very nice. So, actually, there's a couple things I can do with this adjacency matrix in a very convenient way, at least syntactically. I can actually get the degree of a vertex very quickly. So I had to do the exercise before looking at degrees. But here, actually, what we can do is just look at, so I want to know what the degree or the number of neighbors attached to vertex 0. Well, I just should sum up all the elements in this row, right? And so let me show you what I mean. So if I say, well, actually, I'll just do it directly here. If I were to say print mp.sum a axis equals 1, that's going to sum across each row. And so, oops, I should say graph.a. So I see here, okay, if I sum across the row, the first row has 3 1s, second row has 2, third one has 3. And so I say 0 has 3 neighbors, 1 has 2 neighbors, 2 has 3 neighbors, 3 has 2 neighbors, and 4 only has 1 neighbor. So that's a really convenient way to get the degree. So, I could actually just say d is equal to mp.sum graph.a axis equals 1. Oftentimes we call the degree d. Okay. But there's something even cooler we can do with this. So I can ask the question, how many paths are there from u to v that use, and now, yeah, maybe I'll just move this on top here since we have the graph now, just deal with the adjacency matrix. How many paths are there from u to v that use k hops? So, so I'll say, as an example here, A, the adjacency matrix, tells us, so I'll say Aij, or AUV, tells us how many paths there are from u to v that use 1 hop, right? So that's what it means here. If there's a 1 there, it means that I can get from u to v. So here I could get from 0 to 1, row 0, column 1, in a single hop. That's what it means if there's an edge. Okay, but let's think here. What about 2 hops? So 2 hops. So what I want to consider here is, so maybe I'll write this as a loop here. So I'll go ahead and make a little method here. I'll say def get 2 hops count from u to v. So what I would want to do is actually consider a third vertex in between. So going back to the picture here, if I could get from 0 to 1 in 2 hops, there's actually only one way I can do that. Oh, no. Actually, there's a couple ways I can do that here. So one way I can do it is to go from 0 to 2 to 1. So that's 2 hops. I could also go from 0 back to 0 and then over to 1. So I'm looking here, and I think there's actually 2 ways to get from 0 to 1. in the first way, the intermediate vertex there was 2. In the second way, the intermediate vertex was actually 0. So there's a vertex that I have to visit in the middle. I'll call that K for now. So I'll call it K. And so what I'm going to do is consider all possible K's in between U and V. And actually, K could be U itself, right? Because it could have this self loop here. Or K could be V itself. So what I'll do is I'll say, okay, for K in range, A dot shape 0. So the number of rows in A, oops, I should say self.A. The number of rows in the adjacency matrix, or the number of columns in the adjacency matrix, that's how many possible vertices I can visit in the middle. And so what I'll do actually is I'll say, let me have a count here. And I'll say, if there is a path from U to K, and there is then a path from K to V. Right? So like here it was saying, okay, there's a path from 0 to 2, and then there's a path from 2 to 1. So therefore I can get from 0 to 1 in 2 hops by following the first segment on that path and the second segment on that path. So going back here, it would look like that. And then in that case, I would increment the count. Right? And then I'll just return the count here. So let me see if that's the correct answer there. So if I go ahead and print out graph.get 2 hop count between 0 and 1 there, I should get 2 if I've been right about this. And I do. Okay, that's awesome. So I got 2 there. Let's look at another example here. What if I was going to look at the 2 hops between 0 and 3? In that case, I think there's only 1. I think I have to go directly through 2 and then to 3. I don't think I can dilly-dally over here. So let's check. Between 0 and 3, there should only be 1 2-hop path. So if I check that, I get 1. Okay, good. So hopefully that makes sense. And you know, I had you do an exercise like that a moment ago using the adjacency data structure with the adjacency set. But here's the way you would do it with an adjacency matrix. Okay. All right, let's suppose that we want to do this for all pairs of vertices U and V. So I'll say get all pairs 2 hops. So what I'll do is I'll say, okay, I'm going to use this variable over and over again. So let's let n be self.a.shape 0. So what I'll do is I'll loop through all pairs. So I'll say for U in range n, for V in range n, and then I'll just basically copy and paste this loop here. And so maybe I'll make a matrix that's going to be returned. I'll say a 2 hop. So it'll have as many, it'll have the same dimensions as A. And so I'm going to create a triply nested loop where for each pair I'm going to do exactly what I did up above. And now I'll just store the result in a 2 hop U, V. All right? And so then I can return a 2 hop. So let's see about that. If I were to print graph.get all pairs 2 hops, then I get this matrix here. So it's another matrix. Let's just reference our graph for a moment and see what we see. So yeah, supposedly there's actually 3 ways to get from 0 to 0 using 2 hops, which it's kind of interesting. I can see it here. I can go 0, 0, that's 1. I can go 0 to 1, 1 back to 0, or 0 to 2, 2 back to 0. It's telling me there's 2 ways to get from 0 to 1, which I think I already did that example. There's 2 ways to get from 0 to 2 in 2 hops. There's only 1 way to get from 0 to 3 in 2 hops, and actually you cannot reach 4 from 0 in only 2 hops. You're going to need to go through 3. Okay, so this is another matrix. It's like our 2-hop adjacency matrix. Actually, there's something really neat that we can do to compute this. This was the way of writing it out. I'm just saying all pairs. Let me go through and do that thing I did, where I tried each intermediate vertex here. But this is actually an example of something called a matrix multiplication of the matrix A with itself. So I'm not going to go into detail on this. I'll link to a module I made for my AI class that goes into this in more detail. But just to tell you real quick, a matrix multiplication between two two-dimensional arrays is the result that you get. It only makes sense if you have as many columns in the first matrix as there are rows in the second matrix. So in this example, I had a 5 by 3 matrix times a 3 by 4 matrix. And so notice this has 3 columns and this has 3 rows. And the resulting matrix is going to have as many rows as there are rows in the first one and as many columns as there are columns in the second one. And what you do is you take a particular row. So let's say I was looking at row index 2 of the first matrix. And then you take a particular column of the second matrix. And because of the shape constraint that I gave you, you know there's going to be the same number of elements in this row as there are elements in this column. And what you do then is you just multiply the corresponding elements. So that was like that variable k that I had going along there. So I say, okay, you chose my row u in the first matrix. You chose my column v in the second matrix. And now I have this variable k. And so k starts off at 0. And so I'll say, okay, I had this as an if statement before. I said if self.auk is equal to 1 and self.akv is equal to 1. What I can do instead, actually, is instead of writing this like an if statement, I can just write it like a2 hop uv plus equals this times this. So notice it's the same effect, actually. These both have to be 1 in order to accumulate something into a2 hop at this index. So I did it out here by checking these if statements, but I can also just use the numerical properties of 1 and 0 and notice that these would both have to be 1 in order for this to be a 1 and accumulate. So that's like an AND. It's the multiplication here of 1 by 1. That's like an AND. And so now, if I go back to the matrix multiplication, I can see that's exactly what's happening. So I go through my k is equal to 0. I do this times this, plus, and then I go to the k equals 1, that times that, plus the k equals 2, I do that times that. And so you see here the result is 87 for that particular row and that particular column. So row 2, row index 2, column index 3 there, ends up being 87. And so that's how you fill in all the elements of the table. But guess what? This is a super important and well-studied operation on matrices. And so actually, we can just do it directly. NumPy has this here already. So if I were to say print, let's just check, print graph.a. And in NumPy, it's a method called dot. Because actually, this thing that I'm doing here is something called a dot product, where you line the two things up and accumulate the sum of the corresponding products. But anyway, it's called a dot product, whatever. So if I dot a with itself, so here actually I'm multiplying a by itself. I'm doing the matrix multiplication of a by itself. I'm using the same matrix the whole way through, right? In the code I had before, the second matrix could be different. In a general matrix multiplication, that second matrix could be different, but here it's the same one. So if I look at the result, oops, I need to say graph.a.graph.a. Okay, so I look at this, and it's the exact same matrix. But I didn't have to write all this code out here. Okay? All right, but here's the really neat thing that you can do with this representation. That's not quite as readily doable in other representations. So I can keep going, and I can say a3 hop is equal to a2 hop dot dot graph.a. So I could do another matrix multiplication, but this time using a different matrix on the left than on the right. And so I'm saying, okay, this tells me all the ways of getting from u to v with 2 hops. And let me consider another intermediate vertex. So after I've done the 2 hops, let me go through another intermediate vertex and end up at some other vertex here. Well, that's 3 hops total. And I can keep going. I can say a4 hop is equal to a3 hop dot dot graph dot a. So I can actually just keep doing these matrix multiplications. And so let me make a general purpose method here. I'll say def get maybe k hop matrix. And so what I'll say here is the naive version of this. What I would do is I would just multiply on the right by this a for as many times as there are k. So I'll say, you know, my a hop is equal to self.a for I in range k minus 1. A hop is equal to a hop dot self.a, return a hop. Okay. So let's check that again against this. So if I were to print graph.get k hop 2, I should have the same answer there. If I get 3 hops, I see there's actually 7 ways of getting from 0 to itself in this graph with 3 hops. Okay, but what if I were to go back here and say, I actually want to know how many ways are there to get from every vertex to every other vertex using 100 steps? Okay, there's many possibilities, it turns out, in this graph. And it's cool that we can compute that. But actually, there's an even more efficient way to compute this than we're doing here, by using something called a matrix exponential and going back to our good old recursion and memoization. So let me make a method called get k hop efficient here. And let me make the following observation. So if I were to, for example, compute 2 to the, let's say, 21st power, well, I could do that by multiplying 2 by 2 by 2 by 2, 21 times. Or I could actually break it down into 2 to the 10th power times 2 to the 11th power. And actually, I could then break the 2 to the 10th down into 2 to the 5th times 2 to the 5th. And there's, and yeah, and I might as well, right then, I could, break down 2 to 11th into 2 to the 5th times 2 to the 6th. So there's where I have independent and overlapping subproblems. So I'm doing kind of a divide and conquer thing. I'm breaking this down, and I have independent and overlapping subproblems. So what I can do is send along a memory here, and remember, so I'm going to use memoization, top-down dynamic programming. And I'll do the following. So I'll say, okay, my result, we'll say my result is the identity matrix. This was called the identity matrix. If k happens to be 0, that's kind of my default. So if I say, where do you get in 0 hops? It's something called the identity matrix. It's just like multiplying by 1. Okay. But it gets more interesting if k is greater than 0, then let's look here. So first I'll check and see, is k in the memory? Then I'll make my result. I'll just pull that out of the memory. But otherwise, I have some work to do. I haven't seen it yet, so I need to compute what the result is. And so what I'll say is k1 is equal to k floor divided with 2. So imagine that k was 21. So floor divided by 2, that would be 10. And then I'll make k2 be what is left over. So in that example, when it was 21, k2 would be 11. And so now what I'll do is I'll do the matrix with k1 hops, and then I'll do the matrix with k2 hops, and I'll multiply them together. Here I'm using something called the associativity of matrix multiplication. Somehow it doesn't matter where I put my parentheses. I can figure out the 10 hops first, and then the 11 hops first, and put them together to get 21 hops. Or I can add the hops successively like I was in this algorithm. It doesn't make a difference. So it is perfectly legal and fine for me to break this down into how I can get from one vertex to the other with 10 hops, and then consider how to get to an intermediate vertex with 10 hops, and then to the final one with 11 hops. So in other words, I can do these two independently. That's why we have the independent subproblems. So here I'll say A1 is equal to self.get k hop efficient. So I'll say here k1 is the one I want to pass along, and then A2 is what I get when I pass along k2. And so my result here is going to be A1 matrix multiplied with A2. How do I get 21 hops? Well, I visit an intermediate vertex with 10 hops, and then I visit an intermediate vertex with, or I go from that intermediate vertex to my final destination with 11 hops. So 10 hops to intermediate, 11 hops to final destination. And let me remember that so I don't have to redo that work at the end. Okay, so first let me just see if this works. Oh, and of course, don't forget to pass along the memory. Gee, recursive calls there. And I think this should be okay. So let me compare, let me jump down to something a little smaller here. So for 10, I'll compare that to get k-hop efficient. So let me print these both out here. Something went wrong. Maximum recursion depth exceeded. Oh, that's a classic, isn't it? So why would that be happening? Well, it's helpful if I print out what k is here. So let's see where we're getting stuck. Somehow we're getting stuck at the base case. Ah, because I forgot, there is another base case. So if k is 1, well then my result is just a, right? So if I'm asking for 1 hop, I'm just going back to just the original matrix, right? So 1 hop is what my original adjacency matrix was. Okay, let's try it now. Good, and it looks like I get the same answer. Let me go up to 100. And it seems like I'm getting the same answer there too. It's a little hard to tell. So what I can do is I can do the following. I can say print np.all close. So with up to numerical precision, I can ask, are these the same? And it says true. All right. So then let me show you that actually saves some time here. Because the naive way is to do 100 matrix multiplications to consider all possible 100 steps. So if I were to create some kind of member variable here and increment that every time I did a matrix multiplication, let's see how long k-hop takes. And then I'll do it here. I'll say, okay, every time I actually do a matrix multiplication, every time it wasn't in the memory, I actually had to do the work. Let's do that. And so if I look at, so I'll do graph.get k-hop 100 again. And then I'll reset the count. And I'll do graph.get k-hop efficient 100. And then I'll print the count. Count is not defined. I meant to say print graph.count. It's the member variable that I made in graph. Okay, so I have to do 99 matrix multiplications if I'm doing 100 steps naively in the loop. But I only have to do 10 if I'm using this dynamic programming approach with memoization. So just to show you, this is pretty cool. This is a unique data structure for doing very efficient computation of the number of paths that take a certain number of hops between all pairs of vertices. And, matrix multiplication is not as efficient as some other things if what you're doing is just 1 or 2 hops. But once you get a lot of hops, this is a neat little trick that you can use. Okay, and I'd be remiss if I didn't mention just one more thing. This is a little more advanced, and I'm not going to go into the math here, but I'll just mention something. Those who may have seen this before, I would encourage you to think about why what I'm about to show you is true. But let's suppose that I had a couple extra vertices here, a little island over here. And maybe I just add an edge between them. Okay, so I go up now to 7 vertices, and I'll add an edge between the last 2, 5 and 6 there, index 5, index 6. And I could do all this stuff here, but what I'm going to do instead is just look at the adjacency matrix, and I'm going to compute something called the eigenvalues and eigenvectors of this matrix. So let me do that here. Let me just make sure I know what I'm getting. Yep, okay. So let me look in particular at something called the eigenvalues here. So when I look at this, okay, I have as many eigenvalues. Actually, the dimension of this matrix V is the same as the dimension of the matrix A. And what I see here is in each column, I either have some stuff, actually 0 is, let me show a different color map here. And maybe I'll just display the sign of this. So I'll just give it a +1 if it's greater than 0, a -1 if it's less than 0. And then white means 0. So what I see here is the eigenvectors act like indicator functions. Actually, maybe what I can do is I could just say, maybe I'll just say PLT to IM show V not equals 0. Okay, there we go. This is probably clear. This is what I meant to show. So what you see here is these squares give us connected components. Maybe I'll just throw a couple more vertices in here. So maybe I'll add just one more connected component over here. Maybe that'll be between, yeah, so I'll say this is 7, 8, and 9. So I'll add an edge between 7, 8, and an edge between 8 and 9. So now I'm going up to 10 vertices, an edge between 7 and 8, and an edge between 8 and 9. And now let's look at this again. So I get these squares here, and the squares indicate what the connected components are, what the islands are here. Now this is a heck of a lot like what you did in homework 2 on the plant cell assignment. You were trying to find the connected components for the cells. Now this actually would not be a particularly efficient way of doing that for the plant cells. I'll show you another way of doing it, but it's just interesting how little effort it was. Once I filled in the adjacency matrix, which all I had to do for that was literally this. So once I added the edges, I get the adjacency matrix. It's like one line of code basically, and then I get these squares here. So just another way to get connected components. So here I saw the vertices between 0 and 4 are connected. They're on an island with each other. Vertices 5 and 6 are on an island with each other, and then vertices 7, 8, and 9 are on an island with each other. And that's exactly what I have here. Okay, so this is a pretty rad representation. I'm just going to have you do a quick conversion exercise from one format to the other. And then in class, we're going to talk about our first algorithms on topic graphs, which are breadth first search and depth first search. So that's what we will do in class.